or linacs, are used in a variety of industrial and clinical applications, including package and food sterilization, polymerization, and the treatment of tumours. While the name linac is generally applied to the whole apparatus, it correctly refers only to that portion which accelerates electrons. The rest of the device is concerned with bending the beam, modifying the beam by collimating it or converting it into X-rays, or both, supporting the target in the correct location, and providing a power source, mechanical support, cooling, and motion control. The general arrangement has a gantry arm which holds the treatment head in the desired location and orientation. For low energies, a short inline accelerator waveguide can be used. This has the advantage of having the beam energized in the desired final direction and simplifies the design. For higher energies, and particularly those associated with medical treatment, the accelerator waveguide becomes prohibitively long and must be mounted in the gantry arm itself. In this orientation, the beam is energized approximately perpendicular to the final direction and must be bent to enter the treatment head. This is achieved by using bending magnets. The linac itself requires a source of electrons and a source of energy. The electrons are produced by an electron gun situated at one end of the linac. The acceleration energy is delivered in the form of microwaves produced by a magnetron or klystron and propagated down transport waveguides to the accelerator waveguide. In order for this system to work, the entire linac must be evacuated by a vacuum system. Further, because of the power levels involved, many of the systems, including the microwave generator and the accelerator waveguide, must be cooled, usually by a pumped water system. The electron gun uses thermionic emission from a heated cathode to produce a beam that is accelerated towards the anode, which is situated at the inlet of the accelerator waveguide. The cup shape produces an electrostatic field between the cathode and the anode that focuses the beam prior to entry to the accelerator waveguide. Steering coils, mounted as orthogonal pairs, control the inlet direction of the beam to ensure that it is travelling along the longitudinal axis of the accelerator waveguide. The steering coils work by deflecting the charged electrons in a controllable magnetic field. The electrons bend in a direction that is perpendicular to the magnetic field, so that the upper and lower steering coils steer the beam left and right, while those on the sides steer it up and down. Once inside the accelerator waveguide, the electromagnetic field of the microwaves filling the tuned cavities transfers energy to the electrons, accelerating them. It also has a tendency to concentrate the electrons into groups that pass through the accelerator as a bunch. To understand this, consider the forces on an electron in an electric field that varies sinusoidally with position. Electrons are repelled by negative electric fields and are attracted by positive ones. The electrons situated in the negative portion of the field will be accelerated to the right, with those in the most negative region being accelerated the most. The electrons in the positive region will feel a force to the left, which will decelerate them. The net effect is to produce a bunch ahead of the negative crest. The transfer of energy from the microwave field to the electron can be performed by two methods. The first method is to use a travelling wave, where the electric field traverses down the accelerator waveguide and the electrons ride the wave in a similar fashion to a surfer maintaining forward momentum from an ocean wave. The speed of the wave in the waveguide is determined by the cavity geometry and the size of the holes separating the cavities. The first few cavities are smaller and have larger holes, and it is in these sections that the beam is bunched and accelerated to relativistic velocities. In the remainder of the accelerator, the energy largely goes into increasing the electron's relativistic mass, so that the sections are uniform. An alternative method uses a standing wave that is set up by the superposition of the forward travelling wave and its reflected image. The result is an oscillating microwave field that resembles the vibration of a plucked string. The forces on the electrons are as before, however, it can be seen that the field is zero for some of the time. If the cavities are tuned so that the electrons can cross one whole cavity during this time, a constant acceleration can be applied. In this geometry, this is inefficient, as only every second cavity contributes to the acceleration of the electrons. However, These cavities can be moved to produce a side-coupled design. The microwaves pass through all the cavities, while the electrons pass only through the central ones. In this design, the microwave intensity is uniform down the length of the accelerator waveguide, whereas in the travelling wave design, it is attenuated during its travel. Because of this, a standing wave accelerator gives a higher acceleration per unit length, and so can produce an accelerator that is shorter than the equivalent travelling wave design for a given energy gain. However, as the power is uniform down the guide, it requires a higher power microwave, magnetron or klystron to drive it for a given beam power. For both accelerator types, the electrons are subject to forces during acceleration that tend to cause divergence of the beam. To control this, focus coils run along the length of the accelerator waveguide, preventing divergence and bringing the beam to the desired size at a point beyond the exit of the accelerator waveguide. As with the beam inlet, the outlet also has steering coils to ensure that it is travelling in the desired direction. For all but low power devices, the beam must be redirected once it has been energized. The simplest method of achieving this is by using a uniform magnetic field across the beam to give a 90-degree bend. This is not satisfactory, as the radius of curvature of the beam is dependent upon the beam energy. As the beam will always have some distribution of energy, the electrons will tend to disperse, giving an elliptical cross-section. To avoid this, a 270-degree bending system was introduced, which uses shaped pole faces that give a field that grows in strength as the radial distance from the beam inlet point increases. More energetic electrons penetrate further into the bending magnet, but are then subjected to a higher magnetic field, decreasing the orbital radius. The net effect is to produce a beam that leaves the magnet with all the electrons passing through the same point and moving in the same direction. It is a so-called achromatic bending system. An alternative is the 112.5 degrees or slalom magnet. This design is also achromatic, but has other advantages, such as producing a beam that is focused in two directions and also reduces the overall height of the machine. For this magnet to be used, the beam, and hence gantry, must be angled upwards at 22.5 degrees. Once deflected, the beam enters the treatment head for modification prior to final use. The most common modification is to convert the electrons to X-rays by colliding the beam with a suitable target. The X-rays produced are collimated by the primary collimator, which absorbs all but the X-rays travelling in the required direction. The beam is then subject to further modification by using secondary collimators to refine the shape of the beam as required. Additionally, wedge and shaped filters may be introduced to produce a gradient across the X-ray field. Such modifications can produce, for example, a uniform dose along a defined plane of the target object or patient. The treatment head also typically includes a beam monitor for control and feedback purposes and a lamp and mirror to aid with target alignment. The treatment head can be modified in multipurpose devices so that the electron beam itself is delivered rather than X-rays. In this configuration, one or more thin scattering foils are used to broaden the electron beam to give a uniform dose over the defined area. When the linac is used as an X-ray source for X-ray photons above about 10 MeV, the photons can be absorbed by the material in the treatment head, activating them and releasing neutrons or protons. This reaction has a threshold energy, so no activation is seen for X-rays below about 10 MeV. Any neutrons produced contribute to the dose delivered to the target or patient, while any protons produced are usually absorbed within the treatment head, leading to little or no extra radiation hazard. The activated materials in the treatment head can deliver a dose to staff dismantling the head for setup and maintenance. The activated products are usually short-lived, so any radiation hazard during dismantling can be reduced by waiting for several hours after the last irradiation has finished. Because of the short half-life, it is unlikely that a significant build-up of activated material will occur. When the linac is used as an electron source, similar reactions can occur, whereby an electron is absorbed and a neutron is released. The reaction probability for this is much lower than that for X-rays. The dose delivered by a linac is along axes called isocenters, and mechanisms are required to accurately position the target or patient on these. For the medical linac, a patient couch is used that has many degrees of freedom. The couch is supported by a pillar mounted in a revolving base. The couch can be raised or lowered and can itself revolve around the pillar. In addition, it can also slide left and right and forwards and backwards, so providing flexible positioning of the patient. Additionally, the treatment gantry can be rotated about its axis to provide beam access at any desired angle. Where the couch blocks the beam, removable sections are used which support the patient with a mesh rather than a solid surface. The linac is usually situated within a specially designed room so that staff and public doses from its operation are minimised. The room will have a thick primary concrete shield to absorb direct beam radiation and thinner secondary concrete shielded walls to absorb scattered radiation. In addition, the access to the room will typically be through a maze geometry so that the doorway does not have to act as a full secondary shield.